Hello everyone, I am Brihgurish Mishra, PhD student at IIT Bombay, and this is the online session of Elements of Solar Energy Conversion. This is week 11. Okay, so from last week onwards, the solar photovoltaic module has been started. Okay, so in this lecture, I'll cover the lecture 30 and 31. Okay, and till continuity equation, and from PN junction diode, the other TA Mr. Pawan will take the online session. Okay, so in this session we will solve some questions related to the diffuse and continuity equation, and also the penetration depth of the solar radiation. Okay, so first we can look the basics which has been covered in this week. So couple of things like drift motion and drift velocity. This is just to give the summary, okay, of whatever has been covered in this lecture. So what is drift motion? It is basically motion of charge carriers Yes, I'll do problems today. I will I have around 8 problems. Okay, so I'm just giving the basics, okay, the formulas. So motion of charge carriers yeah, so drift motion is motion of charge carriers in the presence of electric field. Okay, so and the diffusion, this is motion due to non-uniformity in the spatial distribution of particles. Okay, so we have looked the Einstein relationship which gives the thermal voltage. Okay, it relates the diffusion coefficient with the mobility of electron as well as holes. So here K is the Boltzmann constant and Q is the charge in Coulomb. Okay, then we saw the generation and recombination. So generation and recombination. So generation of electron hole pairs when a voltage or the solar radiation is illuminated on the semiconductor, and then it recombines, the electron hole recombines after certain time. Okay, that time is the carrier lifetime. Okay, so here this is the rate of generation, del n by del t also equals del p by del t, because number of electrons, rate generation of electrons will be equal to rate generation of holes. Okay, and then we have this carrier lifetime, tau n tau p. This is delta n by r. Here r is the recombination rate, and this delta n, this is the excess carrier concentration. Okay, excess carrier concentration. And then we have seen the continuity equation. Continuity equation, which is simply relates the generation of or rate of excess carrier concentration with respect to the drift with respect to total current density as well as generation rate. So this is del gen n by del x plus generation rate minus del n by tau 1. Okay, and similar for the holes. So let's start with this with the question answer. So the first question is a silicon sample. Here Si I have used for the silicon. Okay, so Si sample is doped with 1 into 10 to the power 6 P means holes, atoms per centimeter cube. Calculate resistivity and conductivity of the sample if the electron and hole mobility are given as 1400 centimeter square per volt per second and 500 centimeter square per volt per second respectively. Consider Ni, which is intrinsic carrier concentration, 1.5 into 10 to the power 10 atoms per centimeter cube. Okay, one thing is similar to previous problems, here also you have to careful with the units. Okay, so make sure every units in the same category, like whether CGS or MKS. So we have given the doped concentration, which is N naught 1 into 10 to the power 16 atoms per centimeter cube. Intrinsic carrier concentration is already given, atoms per centimeter cube. We have also given the electron and hole mobility. So basically questions are the questions are not tricky, and these questions are not very lengthy compared to the solar thermal part. Here you just need to apply formula and find out the values. It's not very tricky, that not tricky means not very complex, like we have, or very lengthy that we need to solve the questions in multiple steps. Here we don't need to do that. It's simple, just apply the formula and get the result. So we have given mu n is 1400 centimeters square per volt second, and hole mobility mu p is given as 500 centimeters square volt second. Okay, so we need to calculate conductivity and resistivity. So as you know, conductivity is inversely proportional to the resistivity, and this we can calculate simply. Sigma equals to Q N naught mu 1 plus P naught mu p. So we have N naught, we haven't given P naught, but we have given Ni. Okay, so we can calculate P naught as in equilibrium condition. In equilibrium condition, the product of N naught P naught equals to Ni square. Okay, so from this relation we can calculate P naught, and this is Ni square by N naught, and Ni is 1.5 into 10 to the power 10 whole square divided by N naught, 1 into 10 to the power 16. So P naught will get around 2.25 into 10 to the power 4 atoms per centimeter cube. Okay, so now we have all the quantities. We have N naught mu n, P naught mu p, and Q you already know. So we can calculate the conductivity sigma. Conductivity, okay, sigma equals to, so 1.6 into minus 19, N naught is 1 into 10 to the power 16 into 1400 plus 2.25 into 4 into 500. Okay, so if you compare these two quantities, obviously compared to this can be neglected, because this is 10 to the power 16 and this is only 10 to the power 4. So clearly we can neglect this quantity. Neglecting this, sigma is 2.24 omega centimeter inverse, and we can calculate resistivity rho is 1 by sigma, which is 0.446 omega centimeter omega centimeter. Okay, so these are the two answers. Now the next question is, the instantaneous carrier concentration in an n-type semiconductor at 2 points separated by 100 micrometer from each other are 1 into 10 power 17 number per centimeter cube and 1 into 10 to the power 15 number per centimeter cube. If the diffusion coefficient of the electron in the semiconductor is 30 centimeter square per second, find out the diffusion current density in the semiconductor. Okay, so this is the problem of diffusion motion. So here we have two sides. At one side the concentration is 10 per 17 and the other side concentration is 10 to the power 15. So clearly there is a difference in the concentration, and because of that difference the electrons will move from higher concentration to low concentration. Okay, so we need to and that will generate a current which is known as the diffusion current. So we need to calculate the diffusion current. Okay, so diffusion current density, this can be calculated using Fick's law. It is Q dn by dx, and this is n is the function of x. Okay, so what are the things given? So we have given dn equals to 30 centimeter square per second. Okay, and the 2 points have also given A, B. So here Na equals to 10 to the power 17 per centimeter cube, and this is the concentration. Okay, and Nb is given 10 to the power 15 per centimeter cube, and the distance between is 100 micrometer. So we can calculate dn of x by dx. This is nothing but we can write it as delta n by delta x, and delta n is simply Na minus Nb by distance between two AB. Okay, so we have this is 10 to the power 17 minus 10 to the power 15 by 10 to the power minus 2. Please note that this is in per centimeter cube, so we also need to put distance in centimeter. Okay, that is why it is 10 to the power minus 2. And here if you can see 10 per 17 minus 10 by 15, this we can write 10 to the power 17 by 10 to the power minus 2. So this is 10 to the power 19. Okay, number per centimeter to the power 4. Okay, so now we can calculate the diffusion current density, since we have all the values. 1.6 into 10 to the power minus 19 into dn is given as 30, and we have calculated dn of x by dx as 10 to the power 19. So it comes 48 ampere per centimeter square. Okay, so this is the diffusion current density. So the next question is, drift velocity of electron in silicon is 10 to the power 5 centimeter per second, and concentration is 10 to the power 17 per centimeter cube. Estimate the drift current density. So again, this is the question of drift motion, and it is a very straightforward question. Okay, so we have given that n is 10 to the power 5 centimeter per second, the concentration. Okay, concentration of electron. sorry, drift velocity, Vd. Okay, Vd is 10 to the power 5 centimeter per second, and concentration is given as 10 to the power 17 atom per centimeter cube. So when we need to calculate drift current density, so it's a straightforward formula. Drift current density J and drift equals to Q N Vd, and you know Q is again same value, N is 10 to the power 5, sorry, Vd is 10 to the power, I should maintain the order, so 10 to the power 17 into 10 to the power 5, so this is 1.6 into 10 to the power 3 ampere per centimeter square. Okay, please note that since this is a current density, that is why it has a unit of ampere per centimeter square. Okay, because it gives the current for a unit cross section area element. The next question is, a piece of semiconductor has the holes diffusion coefficient of 20 centimeter square per second. What will be the mobility of holes in semiconductor at room temperature? Okay, so here we need to calculate the mobility. All these questions I have taken from solar photovoltaic fundamentals and applications, the book written by Professor Chetan Singh Solanki. Okay, so some are examples and some have been taken from the chapter problems. Okay, so yeah, so here what we have given is diffusion coefficient of holes. So dp is given 20 centimeter square per second. Okay, and we need to calculate mobility of holes in semiconductor at room temperature. So you know the relation between diffusion coefficient and mobility is given by Einstein relationship. So we can use Einstein relationship using Einstein relationship. And what is it? So the ratio of diffusion coefficient by mobility is equals to kT by Q. Okay, so we have dp is given, and now T, so we need to calculate at room temperature. So room temperature is considering it as 27 degrees centigrade. So here T is the absolute temperature, T is in Kelvin, so T will be 273 plus 27, that means 300 Kelvin. Okay, and K is Boltzmann constant, it is 1.38 into 10 to the power minus 23 meter square kilogram per second square per Kelvin. Okay, so here we need to convert it into centimeter square. Okay, so you can convert this meter square into centimeter square as 1.38 into 10 to the power minus 19 centimeter square kilogram second minus 2 k minus 1. Okay, and now we already have Q, so we can calculate mu p, mobility of holes. Mu p equals to dp into q by kt, and putting all the values here, 20 into 1.6 into plus 19 divided by k is 1.38 into 10 minus 19, temperature is 300 Kelvin. Okay, so if you solve this, you will get mu p equals to 0.0773 centimeter square per volt second. Okay, so this is the mobility of holes in this semiconductor at room temperature, okay, whose diffusion coefficient is 20 centimeter square per second. Okay, so any question till now? If you have any question, please ask. Okay, so next question. An SI sample is illuminated such that the rate of generation of electrons and holes is 1 into 10 to the power 20 per centimeter cube per second. If the minority electron carrier lifetime is 10 microsecond, what will be the excess minority carrier concentration? Okay, so we need to calculate excess minority carrier concentration. In this case, minority is electron, so this is delta n. Okay, we need to calculate delta n. So what are the things given? Rate of generation of electrons and holes are same, so del n by del t equals to del p by del t equals to 10 to the power 20 per centimeter cube per second. Okay, this is we have given, and we have also given that the lifetime of this minority electron is 10 microsecond. Okay, so tau n is nothing but delta n by r, and this is 10 microsecond. Okay, now this 10 microsecond, this tau n can be written as, so here we need to calculate this delta n, so we know tau n, and here this rate of generation of electrons and holes has been given. Now this this r is the rate of recombination. Okay, so this rate of recombination is in equilibrium condition, it is equal to the rate of generation. Okay, so it is written as tau n equals to delta n by del n by del t. Okay, so we need to calculate delta n, which is tau n into del n by del t. So delta n equals to so tau n is 10 microsecond, but here since we have del n by del t in centimeter per centimeter cube per second, we need to convert this microsecond into second, so it is 10 into 10 to the power minus 6, and del n by del t is 1 into 10 to the power 20. Okay, so delta n is 10 to the power 25 per centimeter cube. So this is the excess minority carrier concentration, okay, for this problem. Now question 6 is, what will be the maximum possible depth of penetration of a photon with absorption coefficient 10 to the power 5 centimeter inverse? So if I have a sample, okay, whose absorption coefficient is alpha, okay, so suppose the radiation intensity hitting at the surface is I naught, so we can calculate the radiation at any thickness. Okay, suppose for this we need to find out the radiation intensity in this semiconductor at a position whose distance with top surface is x. So this can be given as I equals to I naught e to the power minus alpha x. Okay, so this we have given the absorption coefficient alpha is 10 to the power 5 centimeter inverse. So we need to find out maximum possible depth of penetration. So this maximum possible depth of penetration, so for example, if you want to calculate absorption length, okay, so that is so this maximum possible depth of penetration is nothing but the absorption length. Okay, so maximum possible depth of penetration is nothing but the absorption length of the photon. Okay, so this can be calculated as La equals to 1 by alpha. Okay, so this is the length at which the intensity will be 1 by E times of the intensity at the surface. That means this product alpha into x is equals to 1. Okay, so this La equals to 1 by alpha equals to 1 by 10 to the power 5 centimeter inverse. Okay, so this is 10 to the power minus 5 centimeter, and in micron it is 10 micrometer. Okay, so you can say that for this material whose absorption coefficient is 10 to the power 5 centimeter inverse, from surface at 10 micrometer depth, the intensity is reduced to 1 by E times the intensity at the surface. Okay, so the next question is, a semiconductor has sorry, this is 10 to the power 19 per centimeter cube excess hole concentration due to the illumination. The lifetime of the holes is 10 microsecond. When the illumination is turned off, what will happen to the excess hole concentration? Okay, so you can say that like so we have a semiconductor, okay, and when the illumination happens, the excess hole concentration has been generated, and that number is 10 to the power 19. Now the recombination and rate or the lifetime of these holes is 10 microsecond. Okay, so what will happen that as when the illumination is turned off, the recombination will start occur, and after the lifetime of this holes, the initial the x, so there won't be any excess hole concentration. Now the hole concentration will be equal to the initial hole concentration. Okay, that is P naught. So we have, so excess hole concentration given delta P 10 to the power 19 per centimeter cube. Okay, so let P naught equals to 10 to the power 5 atoms per centimeter cube at the beginning of time t equal to 0. Okay, now considering exactly at time t illumination occurs. Okay, so at time t equal to 0, light is shown on sample to generate excess carrier concentration of 10 to the power 19 19 atoms is not 10 to the power 19 per centimeter cube. Okay, and after that illumination is switched off. Okay, illumination is switched off. So now illumination is switched off. So what will happen in this situation? The excess hole concentration will decrease exponentially. Okay, so exponentially as del p of t equals to delta p e to the power minus t by tau p. Okay, and here lifetime is 10 to the power 10 microsecond. So this excess carrier concentration, which is 10 to the power 19, so after elimination it will completely gone, and we will have original, that is 10 to the power 5 per centimeter cube concentration. Okay, so this excess carrier concentration, this excess carriers recombines completely within 10 microsecond, and whole concentration will attain equilibrium values. So if we plot this, okay, so for example, suppose this is carrier concentration. Okay, and this is time in microsecond, and this is in per centimeter cube. Okay, so suppose this is 0, 5, 10, 15. Okay, and you can start here. This is 10 to the power 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Okay, so the initial concentration is 10 to the power 5, so it will be somewhere here. Just a minute. So it will be like this. Okay, so this is your this is P naught, okay, which is 10 to the power 5. Now So at the very beginning, when the illumination occurs, the carrier concentration, excess carrier concentration was 10 to the power 19. So this is 10 to the power 19, and after that it started decreasing, and it decreases exponentially. So but in this short span it decreases very abruptly. Okay, so you will not so it's like that, and this is 10 to the power 5, 10 microsecond, which is the time, the carrier lifetime. Okay, so this is delta p and this is p naught, so it decreases very abruptly, and after the carrier lifetime, the correct concentration is p naught. However, if there is if there is an illumination, okay, like for example there was an illumination and then this excess carrier concentration generated, but then again it removes, okay, the illumination removed, but after certain time, before the carrier lifetime, another illumination was shown, then in that case it will not reach to this p naught, and it will have some value. So it will start, like for example at 5 it again has some illumination occur, then it will go like this. Okay, okay, so this is the graph. So this is the last question I have taken for this class. So when both electric field and concentration gradient are present in semiconductor, both drift and diffusion current flow, which is true. So what will be the direction of each four current components and the direction of carrier motion? So when we have electric field, okay, electric field zeta, then we have drift motion of both electrons and holes. Okay, so because of this there will be two currents, one is due to electrons and one is due to holes. So we'll have Jn and Jp. Okay, and now so this is drift. Now due to difference in carrier concentration, diffusion occurs. Okay, and here again both electrons and holes, because if there is a gradient in carrier concentration, and please note that this is okay, this is in a spatial direction. It's not like at two different time the concentration is changing. No, this is that within the semiconductor there are 2 points which are which has some distance, okay, like some distance apart, and they have a different carrier concentration. Then this diffuse motion will occur. Okay, it's not like that at a particular point at 10 equals to 10 nanosecond there is some concentration ratio, and at 10 equals to 100 nanosecond there is some concentration ratio. So that's not the reason for this diffusion. Okay, this is in the spatial direction. So diffusion occurs both electrons and holes. So again it will have both the current Jn and Jp. Okay, so we can plot a graph like this. So we can draw a table which describes the direction of current as well as carrier force effect. Okay, so suppose the first one is drift, and the direction of electric field in this direction. Okay, so then the So this is in drift case, when there is an external electric field, both the currents will have same direction. Okay, so this is the direction of electron current, and this is the direction of hole current. However, the motion of carrier concentration will be in different directions. Okay, so uh, here, so electron will move in opposite direction. Okay, and holes will move in same direction. Electron motion, hole motion. Okay, so in drift this is the situation. Now I'll talk about the diffusion. Okay, so this is diffusion. So diffusion means we have a concentration gradient. This is n of x, this is p of x. So for this case, the diffusion current of electron is opposite to the diffusion current of holes. Okay, however, for this case, both the carrier motion will be in the same direction. Okay, so this is electron motion and this is hole motion. Okay, so but one thing is clear in both the cases, that the motion of electron is opposite in the current flow direction of the electron due to the electron. Okay, so here J and drift is in the direction of electric field, but the electron motion was in the opposite direction. In the case of diffusion, this electron motion is opposite to the diffusion velocity due to electrons. Okay, so yeah, that's it for today. So if you have any question, please ask, or I'll stop this session here. So here we have taken 8 questions which covers the topic of drift motion, diffusion motion, continuity equation, okay, and generation and recombination of electron hole pairs. So we will meet in the next class. Thank you.